Welcome back to the next video, everybody. Today we're going to prove Theorem TH finally. This is part 2 of the proof of Theorem TH. Last video, part 1, we reduced the complexity of the problem down and we outlined a series of key steps we're going to take throughout the proof. So we're going to get into the details in this video, so let's get started. Let's recall the theorem. It says that the modules L sub t and L sub h that we constructed several videos ago are free T sub sigma modules. And we reduced the proof of this down to the second case of the following theorem that I'll call Theorem 2dim, which says let M be a maximal ideal of T sub z sub L, where I think L here is just some kind of odd prime. Suppose that rho sub frac M is irreducible as a representation, and that either L doesn't divide N, or L squared doesn't divide N, and T sub L is not in frac M. Then the T sub z sub L mod M dimension of the Jacobian J0n bracket frac M is the same as the T sub z sub L mod M dimension of the Jacobian J0n bracket L mod M, and that dimension is 2. And then what we did last video is we summarized the 5 major steps in proving this result, and we dealt with the first step, which was another reduction in complexity. And for brevity, I'm not going to recall the steps here. Please see the previous video. Okay. So instead of proving the step 2 that I outlined last video, I am going to instead show that because T sub L isn't in frac M, the L divisible group, which I'll call cal D, which is J bracket L to the infinity of Q bar localized at M, admits an exact decomposition of the form 0 to D to the R to D to D to the U to 0 into L divisible groups as R bar bracket G sub L modules. So here we're looking for some kind of ramified piece, and here we're looking for some kind of unramified piece as we outlined last video. And then if you're able to prove this, how do you get the corresponding step that we outlined last video? You just set V sub R, which is the thing you want, equal to this guy, D to the R bracket L, and you set V to the U, which is what we want from the step outlined last video, equal to this guy, D to the U bracket L as well. So you just kind of take L torsions. Okay, so how do you build this this exact sequence? First, you know that there's an isogeny from cal D to the product over F of A sub F bracket L to the infinity, where the product is over eigenforms F in S2 gamma 1 of N, and the primes kind of frac L over L in K sub F, which is the number field associated to F, satisfy the property that the corresponding eigensystem mod frac L defined by F factors through the sigma algebra, the Hecke algebra T localized at M. Okay? So because of this, it's enough to work with each of these A sub F bracket L to the infinity separately, since on A sub F, the Hecke operators just act as the eigenvalues of F that we just got done talking about up here. Okay? The first thing we'll do is we'll suppose that L divides the conductor of F. We'll note that the L part of psi of F, the character of F, is trivial, and that the determinant of rho sub F frac L, so the Galois representation attached to F given this prime here, equals chi epsilon, where chi is the L-adic cyclotomic character, and epsilon is a character which is unramified at L. Honestly, I probably should have made epsilon the L-adic cyclotomic character and chi the character unramified at L to keep with standard notation. We claim that A sub F actually has multiplicative reduction at frac L here. So let's prove that. So we'll consider the two coverings from x sub q, so this is our modular curve thought of as an algebraic q curve, to x1 of n prime induced by tau maps to tau, and tau maps to p tau on the upper half plane H. So n and n prime were defined last video over the course of the previous few videos here. So functoriality says that these maps induce a morphism phi from the Jacobian J sub q, so kind of the q model of the associated Jacobian here, to the Jacobian here, J sub 1 of n prime squared, because there are two maps here. We'll let A be the identity component of the kernel of this map phi. It's easy to check that A sub F is actually a quotient of A, and then a quick argument using the neuron model of A over Z sub L shows that A sub F has purely toric reduction, which just means that its neuron model has special fiber with components that are all tori, which is essentially what we're after. Okay. How do you prove this? It proceeds in 2 steps. So first you need a theorem of Raynaud, so theorem 2.5 in this paper here. And that allows you to identify the connected component of the neuron model J sub Z sub L of that Jacobian J sub Q over Z sub L with the degree 0 Picard group of M sub Z sub L, where M sub z sub L is the regular minimal model of the modular curve X kind of over z sub L. So kind of base change to z sub L. And then the next thing you need is this kind of famous result called the rigidity of tori. This is another thing that can be found in, well, you can find it in Raynaud's paper here. You can also find it in Mazur's rational isogenies paper. Okay, and what that tells you is there is a decomposition of the group scheme A sub f frac L to the infinity z sub L in the following way. So you have an exact sequence 0 to t sub z sub L, to A sub f bracket L to the infinity sub z sub L, to E sub z sub L to 0, where what are t and e here? They're L divisible groups of multiplicative, respectively, étale type over z sub L. So it's kind of like you have like a multiplicative type piece and an étale piece. Okay, so I'm not going to go through all of the details of the steps, but I'll just tell you that these are the two kind of major components that you need to prove it. And then once you kind of have what you need here, you can take q bar L points, and that'll give us the decomposition of the Galois representation rho sub f frac L that we seek. And so we'll be done with that step. Okay, that was the argument in the case that L divides the conductor of F. So now let's assume that L does not divide the conductor of F. And then A sub F is a quotient of J1 of n prime. So it has good reduction at L over Z sub L. So this is kind of a standard fact about Jacobians. If F is ordinary at frac L, we're going to consider the connected étale sequence of our L divisible group A sub F frac L to the infinity sub Z sub L. It'll look like this. So 0 to C to A sub F bracket frac L to the infinity sub Z sub L to E to 0. So this is the connected piece. This is the étale piece. Now, the co-kernel over O sub K sub F frac L of the middle term here turns out to be 2. That's an easy calculation. And so it suffices to show that E actually has co-rank 1. Okay. What you do is you show that the co-rank of E is at most 1 first. And the way you do that is you follow Mazur's Eisenstein ideal paper, proposition 14.7, and you appeal to his proposition 9.3 to get the job done. Then you use Eichler-Shimura to conclude that the co-rank must be exactly 1. You can see, for example, Hida on congruence divisors of cusp forms as special values of their zeta functions. This is a good paper to read in general for all this stuff. Propositions 4.4 and 4.17, for example. Okay? Now, that was the proof in the case F was ordinary. If F is instead supersingular at L, one follows the argument of Mazur's proposition 14.2, case 1 in his paper up here, using Diodeny modules to conclude. And then there's also a duality statement if you go back and look at the previous video in step 2 that we have to prove. I'll just say quickly that follows from considering the Weil pairing V cross V to mu sub L, where mu sub L is the group of Lth roots of unity. Okay, so that's not hard to get at all. Okay, there was a step 3. I think there were 5 total steps. So how do we get step 3? You first show that the exact sequence you just got done producing from step 1, 0 to v to the r to v to v to the u to 0, actually splits over r bar. Let's let sigma in the inertia group I sub L be such that omega of sigma generates f star sub L, and we'll let omega tilde of sigma denote the Teichmuller lift, typo there, in z cross sub L of omega of sigma. Since v is finite, there is an h, natural number h, such that v equals the kernel of sigma minus omega tilde of sigma to the n, direct sum, kernel of sigma minus 1 to the h. Okay. It's a quick check that this first summand here is actually just v to the r, while the second is actually just v to the u. We're assuming, because we've already gotten past this point, that v to the r is isomorphic to r bar, and so what we've actually shown is that v to the u is isomorphic to homomorphisms from v to the r to f sub L as r bar modules, which means that v to the u is isomorphic to r bar star, which is f sub L homomorphisms from r bar to f sub L. So this is another way you can think of r bar star here. On the other hand, since L is odd, complex conjugation, which we'll denote by C, induces another decomposition of V as r bar modules, which we will write as V equals V plus direct sum V minus. And so then by Kral-Schmidt, it must be the case that V kind of plus or minus is isomorphic to r bar, and V minus or plus is isomorphic to r bar star as r bar modules if you kind of just compare the two decompositions up here. Okay, I think that takes care of step, well, not quite, that almost takes care of step 3. We do need this dimension to be 1 here. And the ultimate goal is to prove that V is free isomorphic to r bar squared, which was full step 3. So we're not quite done with that yet. But you can observe the following next. the k-dimension of v plus bracket frac m is the k-dimension of v minus bracket frac m. And the reason for that is because the semi-simplification of v bracket frac m is a direct sum of copies of rho sub frac m, which is an odd representation. Okay. This means that both eigenvalues plus or minus 1 have the same multiplicities in v bracket frac m. And you can conclude from this that the k-dimension of r bar bracket frac m must be 1. And so that means that r bar is Gorenstein. For example, you can see Cornell, Silverman, Stevens, page 330 for more details here. Well, that really just tells you that r bar star is isomorphic to r, and v is free isomorphic to r bar squared as desired, which was step 3. Okay. Step 4, we're going to recall from step 2 that the abelian variety A, which was the kernel of the map from J1n prime L to J1n prime squared, and then take this identity component here, which is defined over Q and stable under the Hecke action. So we have this. We'll let B equal J mod A. This is, of course, defined over Q because J and A are, and it's equipped with a T action because J and A are. It also has good reduction over Z sub L, while A has toric reduction over Z sub L. I think we proved this last part in this video, actually. Okay. Since L is odd, if you go to Mazur's rational isogeny paper and you look at proposition 1.3, you get a diagram, which I'll kind of reproduce below here, whose rows are exact sequences of connected finite flat group schemes. And it looks like this. 0 to A bracket L T Z sub L, to J bracket L T Z sub L, to B bracket L T Z sub L, to 0. And then the bottom row is 0 to A bracket L 0 Z sub L, to J bracket L 0 Z sub L, to B bracket L 0 Z sub L, to 0. Where these down arrows here are inclusions. Okay. Exactness can be checked on generic fibers, for example, by Raynaud's theorem from chapter 5, using the fact that L is odd. So that in particular, 1 equals Z is less than L minus 1, which was the condition needed to use this theorem. Okay, so that's how you get that these are actually exact. Okay. Since all irreducible subquotients of kind of cal V equals J bracket L T Q bar L localized at M are ramified, we find that cal V is in V to the R, and what we're trying to prove is actually equality, if you go back and look what step 4 actually is from the previous video. So we have one inclusion here. To check the other inclusion, we'll take the Q bar L points of the above diagram we just wrote, and we'll localize at frac M. Since B bracket L, localized at M is ordinary, the induced rightmost vertical map must be an isomorphism. That's an easy check. By finiteness and completeness, one checks that the induced leftmost vertical map is also an isomorphism, and the way you do that is by rank considerations, by checking on the geometric special fiber, where everything is kind of clearer because A is a split torus over F bar sub L by what we've already proved in this video. And so that gives you the other inclusion, so V to the R is cal V, which is what we're trying to prove. And then there is a step 5, which is to finish the entire proof of theorem TH. The last thing we have to do, given step 4, is show that cal V is free of rank 1 over R bar. First, you pass to tangent spaces and tangent maps in the rows of our diagram. And again, appealing to proposition 1.3 of Mazur's rational isogeny paper, we can produce the following diagram with exact rows: 0 to T sub A bracket L T F bar L, to T sub J bracket L T F bar L, to T sub B bracket L T F bar L to 0. And then on the bottom here, you have just 0 to T to A over F bar sub L, to TJ over F bar sub L, to TB over F bar sub L to 0. Okay. If you localize that diagram at frac M, then the induced leftmost vertical map must be an isomorphism. Again, I mean, this is just, again, because you know that A over F bar L is a torus. And remember, this T thing here was like the largest toric component. Well, if this is a torus, then this is an isomorphism. Okay. Then the induced rightmost vertical map is an isomorphism because B bracket L sub frac M is ordinary, kind of similar to an argument we already gave in this video. That forces the middle vertical map to be an isomorphism. So this map here, after we localize at M. Okay. We now have to prove that Tj over F bar L localized at M is isomorphic to R bar as R bar modules. By Nakayama's lemma, to prove this, we only need to check that the k-dimension of Tj over F bar L mod M dot Tj over F bar L is 1. Okay, so how do we prove that? Since x1n prime L has ordinary double points, this is kind of just a standard fact about this modular curve, we find that if omega is the sheaf of regular differentials on this curve, then we have an FL duality between Tj over F bar L local mod M dot Tj over F bar L and H0 x1 M prime L kind of base change to F bar L. This is bracket frac M. Okay. And then there's a result in Mazur's paper that we've been using kind of this whole proof, which says that this guy is one-dimensional. Okay, so this is one-dimensional. So in other words, we've shown that T sub j bracket L T F bar L is isomorphic to R bar as long as you tensor up to F bar L, because everything was over F bar L here. Okay. However, for any finite flat multiplicative group scheme G, there's a functorial isomorphism between T sub G sub F bar L and the Q bar L points of G tensored up to F bar L. You can see Weil's original paper, page 488, for example, for more details about this. Okay, and so the conclusion is as follows. The conclusion essentially now is that we have what we want, that curly cal V is isomorphic to R bar after we tense up to F bar L. Okay, that's not really what we want, but then you can just use Galois descent to show that cal V is free over R bar, which is what we want. All right, so this concludes finally the proof of step 5, hence the proof of theorem TH, and we are done. And so I think the last thing we need to do to finish up all of the lengthy preparations we've had in preparation for proving R equals T in the general case is prove lemma ihara from video 11.14, which I will do next video. And then 2 videos from now, I will show you the somewhat brief proof, recalling all of the facts that we'll need of R equals T in the general case, given all the complicated stuff we've done so far. And then after that, we'll move into the next chapter, which is the proof of R equals T in the minimal case. So I'll see you all then, and thanks for watching.